Hello, today I'll discuss the similarity analysis, a very important chapter in thermomachinery. The contents of the lecture are similarity analysis, geometric, kinematic, and dynamic similarity. Then I'll discuss about similarity rules. I'll restrict in this lecture to incompressible flows, the relation between xi, phi, and eta. Similarity is the process of describing the behavior of machines of same kind. Suppose from the model test, how can we extrapolate the characteristics of a prototype? In reality, all the design activity after analysis goes through the development of model, testing those models, and then project the test result for a prototype. Immediately, we do not land for the development of prototype. If the characteristics of the prototype is not satisfied, we go back to the analysis and again we carry out the analysis. Thus, the first point that I like to tell, how can we extrapolate the test result of a model for a prototype? And the second one is, suppose for established machine, if its speed changes, if we rescale the machine to design a smaller version, then that means if its size changes, how the characteristics would be. This also can be done through similarity analysis. For similarity analysis, the following three conditions must be satisfied. 1. Geometric analysis similarity. Second, kinematic similarity, and dynamic similarity. What is geometric similarity? Two machines must be geometrically proportional. That means the corresponding ratio, corresponding dimension should be constant. What is kinematic similarity? The flow pattern has to be same. That means the velocity triangle is similar. The ratio of corresponding velocity remains invariant, and the angle of the velocity triangle, the different corresponding angles. Suppose if we take a velocity triangle for the model and that of the prototype, then the angles, corresponding angles, has to be the same. The next one is the dynamic similarity. Suppose for true similarity, equality of Reynolds number must be satisfied. Reynolds number, you see I have given a sketch for frictional coefficient versus Reynolds number. One can easily appreciate that frictional characteristics is dependent on Reynolds number. The Reynolds number same means the frictional characteristics of both the machines are same. Thus, for true similarity, the dynamic similarity has to be satisfied. If the geometric similarity and kinematic similarity, both these two conditions are valid, then the two machines are called kinematically similar machine. Sometimes equality of Reynolds number becomes difficult. So if all the 3 points, that means between two machines, the geometric, kinematic and dynamic similarity are maintained, then these machines are called homologous machines. Equality of other non-natural numbers over the Reynolds number often needs to be satisfied between two machines. Suppose for a propeller, Froude number has to be equal. For high-speed compressors, Mach number needs to be equal. Now let us consider a pump or a compressor which is driven by an electric motor. Since the pump has compression needs to be driven by an electric motor, so its speeds can be adjusted. Similarly, the flow rate can independently be controlled by a throttle valve. So that's what I like to tell, that is speeds of a compressor or pump and the flow rate can be independently controlled. And again, for a certain value of Q, flow rate and speeds, other variables such as heat and power are established. Thus, Q and omega can be treated as control variables, while heat and power can be treated as dependent variable. So thus here I have defined for the turbo machines what are the control variable and what are the dependent variable. In a similarity analysis, the effect of geometric variable must be included, such as size and shape of a machine. Size of a machine is characterized by the impeller diameter and the shape by length ratio, which is represented by L by D. Furthermore, the surface finish must be considered, which is represented here by surface length, small e. Apart from geometric variables, the fluid properties must be considered, such as density, viscosity, and so on. Moreover, we need to distinguish whether the flow is compressible or incompressible. Thus, I like to summarize here. For a similarity analysis, we need to consider geometric variables, fluid properties, and the fluid media, whether it is compressible or incompressible. Let me consider now incompressible flow, and here for a turbo machine, the dependent variables such as energy transfer, efficiency, and power can be expressed in terms of control variable, geometric variables, and fluid property, such as G into H is a function of Q, N, D, rho, mu, L by D, and E by D. So Q and N are the control variable, D, L by D, E by D are the geometric variables, and rho, mu are the fluid properties. Similarly, eta and P also can be expressed as a function of Q, N, D, rho, mu, L by D, and E by D. Now after this, if we do or if we carry out the dimensional analysis following Buckingham theorem, the different non-dimensional group can be established. Thus, after dimensional analysis, what we will get? Xi is equal to GH divided by n square d square equal to function of Qn by d cube rho n d square by mu L by d E by d. These are all non-dimensional groups. Similarly, eta can be expressed as the function of these non-dimensional groups, and p tilde also can be expressed as a function of these non-dimensional groups, where p tilde is equal to p divided by rho nq into d to the power 5. Now here xi is called the head coefficient. Xi is equal to gh by n square d square. This is a non-dimensional pressure, non-dimensional head. Now similarly, what is the non-dimensional flow? That is volumetric flow coefficient is defined by phi. Phi is equal to q divided by n d to the power q. Now phi, please follow the right of here. You will appreciate the phi can also be expressed as Cz divided by u. Cz is the meridional flow through the machine, which is connected to the volume flow rate q. Furthermore, what is rho n d squared by mu? Rho n d squared by mu is a form of Reynolds number. Similarly, p tilde is p by rho nq d to the power 5 is the power coefficient. So thus here, after dimensional analysis, what we have got, that xi, eta and p tilde is the function of some non-natural group. They are flow coefficient, phi, Reynolds number, and some geometric variable, which is L by d and E by d. Now, for geometrically similar machines, the shape parameters L by d are constant, and thus they can be omitted from the above relations. Again, if dynamic similarity is maintained above the geometric similarity, then the effect of Reynolds number can be ignored. Thus, the functional relationship for geometrically similar machines at high Reynolds number, neglecting the effect of surface roughness, can be expressed as xi is nothing but function of phi, eta is function of phi, and tilde is function of phi. So thus, in brief, for a geometric and dynamic similar machines, that means in a strict sense, if the machines are homologous, then xi, eta, and p tilde can be expressed as a function of phi. Here I will establish the relation between psi, phi, and eta. Let us first consider a pump or a compressor. The net hydraulic power is given by pH is equal to rho Qg into H. Then efficiency eta can be defined as pH by P, where P being the shaft power. Note that for a pump or for a compressor, shaft power is greater than the hydraulic power. So now through some algebraic manipulation I have written as P equal to 1 by eta within the bracket Q in d cube divided by Q divided by n d cube. Again another bracket GH divided by n squared d squared, and then multiply by rho in Q d to the power 5. Now if you remember, this Q divided by n into dq is nothing but phi flow coefficient, and GH n squared by d squared, this group is nothing but xi. So thus P tilde is equal to P divided by rho in Q d to the power 5 would become xi into phi divided by eta. So thus for a pump or a compressor, I can write P tilde is equal to xi phi divided by eta. Whereas for a turbine, eta can be defined by P divided by pH. Now here, hydraulic power is supplied to the machine, so hydraulic power is greater than the shaft power. So thus eta can be defined as P divided by rho Q G into H. And thus one can easily prove here that P tilde here is equal to eta into xi into phi. Thus, in nutshell, for a pump or compressor, P tilde will be equal to xi phi divided by eta. For a turbine, P tilde would be eta into xi into phi. Thank you for listening.